Okay, today we're going to be starting to look at electric fields. So we know that two charged particles interact with each other. And they can interact with either an attractive or a repulsive force. And so say we had a positive charge and a positive charge. These are going to repel each other. A negative charge and a negative charge will also repel each other, and a positive charge and a negative charge, oops, that's a very small negative charge, and a negative charge will attract each other. So opposite charges are attractive, and particles of the same charge will repel one another. It's, as we can see in our little diagram here, that the charges don't need to touch each other in order to interact. So this charge here is being repelled by this charge here, and vice versa. But they can't, they're not touching. How would they, that brings us to the question of how does this charge know that this charge even exists? And this brings us to the whole concept of field lines and of electric fields. So this, each charge has an electric field around it. All charged particles have electric fields, and when another charged particle comes into that field, the field all, so this there'll be a field radiating out from this charge, and a field radiating out from this charge. And when these fields come into contact with one another, there's an interaction between the fields, and that therefore the particles will then respond to the interaction between the different electric fields. And when we're talking about electric fields, pay attention to note similarities in the mathematics regarding magnetism and also gravitation, because the concepts are strikingly similar. So that just bear that in mind as we're going through this, and as we in subsequent lessons when we're talking about magnetism and when we're talking about and remember when we talked about gravitation. There's a lot of similarities, which it's important just to be paying attention to these ideas. Now, as we move forward, we're not going to think about charges as like these big balls. We think about charges as being point charges. So this means they are infinitesimally small. Basically a point. And we in physics we always talk about a charge being like a point charge. So it's just something to bear in mind as we're moving forward, that when we talk about a charge, we're talking about these point charges. Now let's look at positive charge, and again I've drawn a big circle, but this is what we would be thinking this is a point charge, and the field lines radiate out. Now see each point here where's a field line, you can think of that field line coming out at right angles to that point charge. So for a positive charge, we have our field lines, and they come out, and the direction of the field is away from the charge. Because when we think about field lines, we're considering what would be happening to a positively charged particle interacting with this field. So the field lines show the direction of a positive, the direction, a positive charge would, would follow in the electric field. And that's important when we talk about the field, when we draw field lines. And every time we draw on a field line, we're always thinking about that they're showing the direction of a positive charge, what that positive charge would follow in this, in this electric field. So if we were to draw it for a negative particle, that is far too big, we'd just have the opposite. It would look identical, but this time our field lines, the direction of the field is going towards the particle, the point charge. Now, these individual field lines only show, the field lines only show the direction. They do not show the force on the particle. So if you've got the little particle, the field lines don't show the force on a particle in the field. However, the closeness of the field lines indicate the relative strength of the field. So if there's more if you were to draw more field lines, that would show that the electric field associated with this point particle was stronger than, say, if we had, this is another one here. So the field lines on this one are closer together than on this one. Therefore, this electric field is relatively stronger than this electric field. So drawings, these sorts of diagrams, they have limited, give us limited information, but they're more useful if we want to draw what's happening to an electric field when we've got more than one charged particle present. So if we have, say, two positively charged particles of equal strength, and again the field lines are still showing the flow of a positive particle within the actually no, we'll do a positive and a negative one to begin with. So we've got a positive and a negative particle. So we're going to have that flow from the positive to the negative, and we can see how this would be. So this is kind of like your halfway point. Actually, we'll draw it as a straight line. Try and draw it straighter than that. It's a bit wonky. There we go. And then it's going to come out. That's the wrong direction. So that is the electric field between a positive and a negative particle. Now, again, this only shows the direction of the field. If you want, what we can do is we can mark in using a dash. We're going to use a dashed red line, and that will show us the position within this field where the field is of equal strength. So think about these dashed lines a bit like the contour lines round a hill. If you think about if you're going on, if you see a map, the contour lines show the positions of equal height. Well, these are like contour lines showing where the electric field has equal magnitude. And you can see that for the positive and negatively charged particle, the contour line, the positions of equal strength are going to be more tightly packed in the area that is closest between the two charged particles, and then as you get out here, they get pulled out a bit more. Similarly, we can actually get another page up. For we can have for two positive charged particles, we'll have something that looks a bit more like this. Nope. You can often be asked in exams to draw field lines. It's important that you just pay attention to make sure you draw your arrows in the correct direction, because it's easy to just as you're drawing to make a mistake there. So this would be for the field for a positive and a positive electric field. Now, it's to be noted that the electric field is experienced in 3 dimensions. So we've been drawing them in 2 dimensions, but obviously these are going to be inhabit 3-dimensional space. Another thing to note is a quick digression into Coulombs Law. So Coulombs Law gives us the force between two charged particles. So F equals some constant K, Q1 times Q2 over R squared. So if you've got Q1 and Q2 and their distance apart is R. So what this tells us that the force, the electric force between two particles is directly proportional to the size of the force, the size of the charge of the particles, but is inversely proportional to R squared, the distance squared. And just if you look at this, just note the similarities between Newton's law of universal gravitation, which you'd in Newton's law of gravitation, you'd have the masses of two objects, and again they are inversely proportional to the distance squared. Now k, for two charged particles in a vacuum, k would be 1 over 4 pi epsilon, where epsilon is the permittivity of free space. And if you remember from our last lessons, we were talking about the speed of light and how that is related to the permittivity and the permeability of free space. You see this value epsilon has appeared again in our in another context. So just note that as something just to file off in your brain. So this is not in the course, but it's an important thing just to, this is an important concept just to understand, because it gives us an understanding as to what's happening when we're thinking about electric fields and charges. Now, electric field strength. And again, as we're talking about electric field strength, just also consider the parallels between gravitation. So the force, oops, oh, that's not my spell for us, just rewrite that, that was rubbish. The force on a particle with charge Q in an electric field is given by F equals Q E, where E is the electric field strength. And I'm just going to write quick as a wee side note, think about the equivalent equation for magnetism. W equals mass times G. So that these are similar concepts, similar ideas. Now, back to electric fields. So we can rearrange this for the electric field strength is equal to the force times Q. Now, we just were talking about Coulombs Law, where the force is equal to this constant K Q1 Q2 over R squared. Now, if we use this equation here and substitute in for F, so F is the QE equals K Q1 Q2 over R squared, and then we have the field strength is going to be equal to Q1 Q2 over R squared, Q here, but the Q is the same as one of these charges, so we can say Q, the force of the charge of the particle, and so in this, so let's just draw what we've got. We've got we'll call this Q2, and we've got, and Q2 is making this electric field, and then you've got this particle Q in this electric field, so Q is equal to big Q1, so that then gives us, so that one and that one will cancel, so E is equal to the constant K Q over R squared. So from this, what we can state is the greater of the charge, this charge here, the greater the electric field strength around it. So if we've got this electric field, so this is our electric field. I've not drawn arrows in because we've not stated if it's positive or negative. So our electric field, the strength of this electric field is going to be proportional to the size of this charge. And that's kind of intuitive. The calculation for electric field strength leads us on to what happens when one of the particles has a greater field than the other. So what if we have a situation where we've got some particle, it's got positive, and we're just going to put positive 1 charge, and then we've got another one here which is got twice as much charge, and we'll call that positive 2. So this is where this charge here is going to have a stronger field. So the field from the more strongly charged particle have a greater sphere of influence than the other one. And therefore, in other words, this charge is going to control more of the space around the two charges. So the field is going to kind of, and remember, the closeness of the field lines gives an indication of the relative field strength as well. So we've got direction and the relative field strength. And then this one's is not going to have as much control because it's got a smaller, less charge, and the field lines will be more spread out as well because this charge is less. Now, we've been talking about point charges almost like as if they were little kind of billiard balls. Any charged particle, regardless of shape, there's an electric field around any body, regardless of shape. So let's consider parallel charged metal plates. So something like this. We've got metal plate here, and we're going to see this is attached to the positive charge, and a metal plate here which is negative charged. So this down here is all positive, and here is all negative. And what will happen is, in the middle of the plates, you will have a uniform field. Of parallel lines. And the field will be of equal value. At either end of the plate, there is increased. If the charge on either plate is increased, the field will increase. At the edges of the plate, the lines will bend, kind of like this. This is because the field still has an effect in the areas that surround the two plates. So I hope that helps.